Okay, this is a recording of the Chapter 2, Section 2A, Limits Involving Infinity. Okay? Don't worry about the date that you see up here. Obviously, this is from last year. Okay, I'm going to talk through some of it on the screen, then I'll also go to the camera at times as well. So we already talked about this limit notation, so hopefully we know how to read this. In this particular case, we would be saying the limit as x approaches infinity of f of x equals the limit as x approaches infinity of a constant always equals the constant. If you think about a horizontal line, the limit as x approaches infinity, it's that line, it's that value. Okay? So the limit as x approaches really plus or minus infinity of a constant is always just the constant value. If f is the reciprocal function, this is a big one here. And I know Mr. Hearn talked to you about this. The limit as x approaches infinity of f of x of this reciprocal function, the limit as x approaches infinity of 1 over x, always equals 0. As the denominator grows without bound, if the denominator grows faster than the numerator, then the limiting value will always be 0. You'll get closer and closer and closer to that horizontal asymptote at 0. This is directly connected to the concept of horizontal asymptotes. Just think about this. The degree on the bottom is larger than the degree on the top. Therefore, as x goes to infinity, the function's going to get closer and closer and closer to 0. So they're one and the same. When we're taking the limit as x approaches infinity, when the degree on top is less than the degree on the bottom, or just if the degree in the numerator doesn't grow as fast as the denominator. Anytime the denominator outgrows the numerator, that limiting value is going to go to 0. Properties of finite limits as x approaches infinity. If L sub 1 and L sub 2 are real numbers and the limit as x approaches infinity equals these values, all this is saying is this sum and difference rule here. They work the same as they did in the last section. That if you're taking the limit as x approaches infinity of two functions added together, you can find their separate limits and add them together. If you're subtracting, find the separate limits and subtract. If you're multiplying two functions, find the separate limits and multiply. And if you have a constant multiple, find the limit of the function and then multiply by the constant. It also works for a quotient, again, provided that the limit of the denominator does not equal 0. All of these properties hold for negative infinity as well. Notice that negative sign right there. Okay? The function g is an end behavior model. You're going to see this term a lot. End behavior model. Okay? I'm going to highlight that word for you quickly. End behavior model. So we've already talked about some end behavior models. You would have talked about end behavior models when you found horizontal asymptotes and slant asymptotes in pre-calculus. But now we will also have other types of end model behavior, like quadratic end model behavior, cubic end model behavior. Okay? This says the limit as x approaches plus or minus infinity of f of x over g of x equals 1. When g of x is not equal to 0, obviously, for absolute value of x, okay, large, or the limit as x approaches plus or minus infinity goes to 0 when g of x equals 0. I would not worry too much about this right here. Okay? This theorem is going to be important though. If f of x equals this is I know there's a lot of letters in here, it can be confusing. This is just an arbitrary polynomial function. Okay? Where this first term here is called the dominant term because it has the largest exponent, because the exponents are going down by 1 in polynomial function. Then the dominant term is the end behavior model. So if we had f of x equals 3x to the 5th minus 4x to the 4th plus 2x cubed minus 7x plus 5, as x goes to plus or minus infinity, the only term that's going to matter is going to be that first term, the most dominant term. That is the end behavior model. Here, this is what's really important. This part right here. So I'm going to highlight some areas and hopefully you highlight it as well. A line, y equals b, that's a horizontal line. Y equals a constant, is a horizontal asymptote of the graph of a function y equals f of x if either one of these are true. The limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. It doesn't matter if we're going to infinity or negative infinity. Okay? Think about it. This is how we determine whether we have a horizontal asymptote or not. As x gets really large, if the output is getting closer and closer and closer to a constant value, that is the horizontal asymptote. And it doesn't matter if x is going to positive infinity or to negative infinity. Okay? Now that's different than this, a vertical asymptote. Notice it's x equals a constant, a vertical line. And we have vertical asymptotes when the limit as x approaches that x value from the left goes to plus or minus infinity, or the limit as x approaches that x value from the right goes to plus or minus infinity. There's a huge difference between these two. For horizontal asymptotes, we're finding the limit as x approaches plus or minus infinity to see if the value approaches a constant, where for vertical asymptotes, we are seeing as we get closer and closer and closer to that x value from the left or from the right, does the graph take off to positive or negative infinity? That's how we determine a vertical asymptote. This is the formal definition. You found horizontal and vertical asymptotes in the past. This is how we formally define it using calculus notation. This summarizes the end behavior model. We're going to see this end behavior model notation a lot. Let f of x be p of x over h of x, be a rational function, and q of x and r of x be the quotient and remainder. So if we were to do long division, when we do that, this q of x plus r of x over h of x, the remainder portion is going to go to 0 because the degree on top is going to be less than the degree on the bottom. So this q is called the end behavior asymptote. This is how we got slant asymptotes last year. We did long division and then we canceled off the remainder over the divisor. But now this q of x could be quadratic. It could be cubic. If the degree in the numerator of f is 2 degrees larger than the denominator, then we'll end up with a quadratic end behavior model. If the degree in the numerator is 3 degrees larger than the degree in the denominator, if this is a quartic over a linear, we'll end up with a cubic end behavior model. Okay? But this is the summary that you really need to know right here. If we're talking about this rational situation, this is a review of pre-calculus right here. If the degree in the numerator is less than the degree in the denominator, then the limiting value is always 0, and y equals 0 is the horizontal asymptote. All we have to do is find the limit, and y equals that limiting value is going to be the horizontal asymptote. If the degree in the numerator equals a degree in the denominator, then the limiting value is going to be that constant. Remember, that constant is found by taking the ratio of the coefficients of the highest degree term in the numerator over the coefficient of the highest degree term in the denominator. And y equals that constant is the horizontal asymptote. And if the degree in the numerator is larger than the degree in the denominator, then the limiting value is always going to be either plus or minus infinity. We just got to decide which one. And y equals this quotient we just talked about up there is going to be an end behavior asymptote. If the degree in the numerator is 1 larger than the degree in the denominator, this will be a slant asymptote, a linear asymptote. If the degree in the numerator is 2 larger, this will be a quadratic end behavior model. If it's 3 larger, it'll be a cubic end behavior model. Okay? So let's take a look at this, and I'm going to actually go to where I'm processing some of this instead of just looking at the answers so that you can see how some of this works out. All right, taking a look at this first example, use algebra to find the limits of the function defined by expression as x goes to infinity, as x goes to negative infinity, and then support graphically. Remembering that the support graphically part, I expect that you can type these functions into your calculator and you can check to see that your limits make sense. I'm not going to type each one of these into the calculator. I can certainly do more of that later on if people feel that they need it. But hopefully people can type this in, especially using the fraction key that you have now when you go alpha y equals. So let's just start out with this. The limit as x approaches infinity. Make sure that we recognize we're really looking at an asymptote here. Okay? There are a lot of books that will show detailed work on how to verify this. They're not going to expect you to be able to have to do that on the AP test, so we're not going to do it. We're going to use prior knowledge. We're going to use the fact that we know that the degree on top is the same as the degree on the bottom. They're both linear functions. The numerator is aligned, the denominator is aligned. So in order to find the horizontal asymptote, the degree on, I just look at the coefficients of the highest degree terms. Okay? So y equals 2/5 is going to be the end behavior model. Just understand that horizontal asymptotes are one type of end behavior model. Well, if that is the case, then the limit as x approaches positive infinity here is going to approach that horizontal asymptote. And the limit as x approaches negative infinity is also. Okay? So what type of end behavior model do we have? This is a horizontal asymptote. Okay? So horizontal asymptote. That's what we're going to write here. Okay? So next problem. Now the degree on top is less than the degree on the bottom. The numerator is a linear function. The denominator is a quadratic. Degree 1, degree 2. The denominator is going to grow much faster than the numerator. When I square a large value, that's going to grow much faster than the top. Anytime the bottom grows faster than the top, the limiting value is going to be 0. Whether I'm going to positive infinity or negative infinity is not going to change here. The end behavior model is y equals 0, and we always have to say y equals when we're given an end behavior model. And again, this is a horizontal asymptote. Okay? So, let's take a look at this one. Now, there's a little bit more work that we have to do when the limit as x approaches infinity or negative infinity is this situation. The degree on top is larger than the degree on the bottom. We could do long division all the way out to find this limiting value here. But I don't want you to do that. To find the limiting value, it's either going to be infinity or negative infinity. We just have to decide which one. And I really only have to look at the ratio of the dominant terms. So if I look at 3x squared over 4x, those are the dominant terms. I can cancel an x, and I get 3/4 x. And then I ask myself, if I plug in 10 or 100 or 1,000 or 1,000,000, this is just getting bigger and bigger and bigger in the positive direction. This goes to infinity. But if I plug in -10, -100, -1,000,000, it's getting larger and larger in the negative direction. There it is. If the degree in the numerator is 1 larger than the degree in the denominator, it's always going to be a slant asymptote. And a slant asymptote is a linear end model behavior. Okay? Now, I shouldn't have written that there. I'm actually going to write this down here. Okay? That's the type. It's a slant asymptote or linear asymptote. But in this problem, I ask you to identify the end behavior model. How do we determine the end behavior model? We have to do long division. 3x squared minus 6x. I'll put a plus 0 here because I might need that space. And I'm going to divide by 4x minus 8. I can remember algebra teachers asked me in the past, when do we ever use long division? Use long division right here. Okay? What do I have to multiply 4x by to get a 3x squared? Well, I'm going to need an x for sure. Okay? I need to be able to cancel the 4 and have a 3. So I have to multiply by 3/4 x. When I multiply 3/4 x times 4x, the 4's cancel. 3x times x is 3x squared. That's exactly what I need. If I take 3/4 x times negative 8, the 4 and the 8 cancel. It's negative 2 times 3 is a negative 6x. I never say subtract when I do these problems. I always say change the signs and add. That's how I'll verbalize it. Because students inevitably will subtract here and then add here. So change the signs and add, and I get a remainder of 0. Okay? I get a remainder of 0. So the end behavior model here is just going to be y equals 3/4 x. Okay? That's how that one looks. Let's take a look at D. So there isn't too many that you're going to have to do this on. But just remember, if the degree on top is larger than the degree on the bottom, we do have to do long division to determine the end behavior model. The remainder always goes to 0, so you just don't worry about the end behavior. Or you can just get rid of the remainder over the divisor. D. Most of them are like this. The degree on top equals the degree on the bottom. The degree in the numerator is 3. The degree in the denominator is 3. So I look at the coefficient of the highest degree terms. Sometimes it's easier just to determine the end behavior model first. Y equals negative 2/3. So the limit as x approaches infinity is going to be negative 2/3. The limit as x approaches negative infinity is going to be negative 2/3. Whenever it's y equals a constant, whether it's 0 or some other number, it is a horizontal asymptote. Okay, so we just fill that box in. E, the degree on top is 0. A constant term has a degree of 0. The degree in the denominator is 3. The degree in the numerator is less than the degree in the denominator. Therefore, the limiting value is 0 because that is my horizontal asymptote. Okay? And again, this is a horizontal asymptote. Okay, we'll move on to the next topic. Okay, the nice part about these problems is the directions on the worksheet are going to read, find the following limits by a convincing method of your choice. That's nice. So the convincing method of your choice can be just provide the answer. That's okay. Might be easier to actually read this on the PDF, but I'm going to do it here because I want to show you one of the methods is to simply sketch a quick graph. So the limit as x approaches 2 from the right, remember that's how we read this. The limit as x approaches 2 from the right of 1 over x minus 2. So a convincing method of your choice would be to do a quick sketch. The vertical asymptote is x equals 2 because 2 makes the denominator equal 0. And it does not cancel with a factor in the numerator. The degree on top is less than the degree on the bottom, so we have a horizontal asymptote of y equals 0. And here's why I want you to know the difference between a pole and a volcano. It makes a huge difference on these problems. I just have to pick one point. If I pick 3 in for x. I put 3 in for x here, okay? If I plug 3 right here, 3 minus 2 is 1, 1 over 1 is 1. That 1 point, now that I know how rational functions work, and we've talked about them in chapter 1, I know it's going to approach the asymptote here, and it's going to approach the horizontal asymptote here. Now the beauty of this is because the denominator I know that the vertical asymptote comes from a factor raised to the first power. This is x minus 2 to the first power. It has to be a pole. If this is x minus 2 quantity squared, I would jump across the asymptote, and it would be a volcano. But since it's a pole, I know I have to slide down the pole and start again. That is enough for me to get a quick graph. And now the limit as x approaches 2 from the right takes off to positive infinity. As I'm approaching an asymptote, and I should be able to identify right away that I'm approaching an asymptote. I'm approaching a number from the right or from the left. And I know it's an asymptote at that number because x equals 2 makes the denominator equal 0. The answer is either going to be positive infinity or negative infinity. You just have to figure out which one. Now, I would say you can do this without graphing it, but there's a lot of students who will just sketch a quick graph to make sure. And here's why. If I just pick a number really close to 2, but to the right of 2, let's say this, 2 1/10, that's pretty close. 2 1/10 minus 2 is 1/10. 1 over 1/10 is 10. Let's look at 2 and 1 over 100. 2 and 1 100, that's really close to 2. Subtract 2 is 1 over 100. And 1 over 100 is 100. It's getting larger and larger and larger. So you can do it without graphing. But there are a lot of students who prefer to just do a quick sketch because they get really good. They become really proficient at sketching these. So I'm going to do it both ways. Let's take a look at this one. Now it's a little bit different here. We're still taking the limit as x approaches 2 from the right. But watch what happens here. Our vertical asymptote is x equals 2. Dot that in using my highlighter here. But the horizontal asymptote, the degree on top, the degree in the numerator, equals the degree in the denominator. They're both linear functions. So I look at the coefficients of the highest degree terms. 1 over 1 is 1. Plug 1 point in. I always think it's easier to plug it the value to the right of the vertical asymptote. So if I plug 3 in, for x, right here and right here, 3 over 1 is 3. So if I go to the right 3, I'm going up 1, 2, 3. That's enough. That is enough for me to know that this picture is going to look like this. Okay? And I know this is a pole. It's x minus 2 to the first power. It's not x minus 2 quantity squared. So I have to slide down the pole before I start again. Now I could pick another point over here and be real detailed, but in terms of finding the limiting value, this is going to be enough. The limit as x approaches 2 from the right goes to positive infinity. So you can just say infinity or positive infinity, either way. If this would have been a negative sign here, and it probably be the same problem in your worksheet, but that'll be a negative sign. As you approach 2 from the left, this goes to negative infinity. So when you're dealing with poles, whether you approach the asymptote from the right or the left, one's going to go to positive infinity, one's going to go to negative infinity every time you have a pole. And if you can identify it right away, that's why I want you to know that terminology. Where a volcano, whether you approach from the right or from the left, if it's a volcano look, it's either going to go to positive infinity or negative infinity, but they'll both be the same. Let's take a look at C. And again, some of this, I wish it was blown up a little bit more. It could be hard to read. But the degree on top is less than the degree on the bottom. Remember, a constant has a degree of 0. So I have a constant over a linear. The bottom is going to grow faster than the top. So the horizontal asymptote is y equals 0. And remember, I told you we're going to get plenty of practice on these rational functions throughout this chapter. But the vertical asymptote here is negative 3. 1, 2, 3. And I know this graph is small. They'll always be blown up for you on tests and quizzes. Okay? Let's pick one point. I think it's best to pick a point to the right of the vertical asymptote. So the vertical asymptote's -3. Let's just throw -2 in here. Because look, -2 plus 3 is 1. 1 over 1 is 1. There it is. That 1 point is enough to know I'm going to approach my vertical asymptote this way. I'm going to approach my horizontal asymptote this way. You could graph a few more points to see it if you'd like. Okay, always putting arrows on the end of it. Okay, but this is, again, a pole. It's x plus 3 to the first power. It's not x plus 3 quantity squared. If it was x plus 3 quantity squared, I would jump across and go here. But I slide down the pole to start again. And I just have to be careful. I'm approaching -3 from the right. So I'm getting closer and closer and closer to -3 from the right. It's going to infinity. As I approach -3 from the left, if that little plus sign was a minus sign, that would go to -infinity. Now, let's talk about being able to just think about these again. Let's go back up here. Let's pick a number to the right of 2, but really close to 2. Like, let's just use a decimal, 2.1. 2.1 over 2.1 minus, well, that's 0.1, which is 1/10. When I multiply by the reciprocal, 2.1 times 10 goes to 21. Let's think about this. 2.01. That's really close to 2, but to the right. 2.01 minus 2 is 0.01. Multiplied by the reciprocal is 201. It's getting larger and larger and larger in the positive direction. That's why it goes to positive infinity. Let's talk through this one here quick, just so that we do understand that you do not have to graph this every time. As long as you can get the answer correct, I'm fine with that. If I approach -3 from the right, I got to think a little bit. -3 from the right is going to be -2.999. -2.999 plus 3 is going to be positive 0.0001, or 1 over 1,000. Flip is 1,000. That's why it's going to infinity. Okay, so the first three all go to positive infinity. What's going to happen with this one? It doesn't change a whole lot, except does this vertical and horizontal asymptote situation here, now that this horizontal asymptote is y equals 1, does that pose a different problem? Notice the horizontal asymptote is y equals 1 because the degree on top, same as the degree on the bottom. Coefficient of 1 over 1 is y equals 1. Vertical asymptote is at x equals -3. There it is. Okay? Plug in 1 point to the right of the vertical asymptote. Picking 1 point to the right of the vertical asymptote, like -2. -2 over -2 plus 3. -2 over 1 is -2. Oh, now I'm here. Right? As a matter of fact, you could plug the point 0 in if you want. 0 over 3 is 0. There's another nice point. Now the graph is here. It is a pole. The denominator is still raised to the first power. X plus 3 to the first power. So climb the pole before I start again. There's a nice graph. The limit as x approaches -3 from the right this time goes to -infinity. Okay? Let's talk about numbers. So pick a number really close to -3, but to the right of -3, like -2.99. This is -2.99 plus 3, which is positive 0.001. 1 over 1,000 flip is going to be -2,900. It's going to be a large negative number because you get a negative over a positive. So this horizontal asymptote change had a big impact on whether this limit went to positive infinity or negative infinity. But if you know the difference between a pole and a volcano, and you can sketch a quick graph of these rational functions, like you did in pre-calculus and in chapter 1, a graphical approach is just fine as well. Okay, typically in the past we've had 3 problems on the test that you have to graph, like this. One in which the degree in the numerator is less than the degree in the denominator, one in which the degree in the numerator is the same as the degree in the denominator, and one in which the degree in the numerator is larger than the degree in the denominator. I won't have you graph anything in which the degree in the numerator is larger than the degree in the denominator unless it's just one larger. It's a slant asymptote. Let's start with this one. First thing we always want to do is see if we can factor to determine our vertical asymptotes. And I did try to give you one that's a little bit more involved here. This factorization, again, 2 times -5 is -10. Are there 2 numbers that multiply to be -10 and add up to be +3? 10 and 1 is not going to work, but if I have a +5 and a -2, that will work. I'm going to make the outside multiply to be -2. I'm going to put an x here and a -2 there. There's the outside. Okay? Let me say that again. I'm going to make the outside multiply to be -2, and I want to use the largest factor from x that I can use. So I'm actually going to put a 2x here, because I can make the 2x work, and a -1 there. Remember, the key is I always want to use the largest factor from here that can make it work. So I should have used the 2x. That's a -2. First times first to get the first, 2x times x to get 2x squared. Last times last to get the last, 2x plus 5. Okay? It's very important that we can factor on these problems because I have 2 vertical asymptotes. X equals -5/2 makes this factor equal 0, and x equals 1 makes this factor equal 0. So I have 2 vertical asymptotes. X equals 1 and x equals -5/2. The end behavior model. Remember, a horizontal asymptote is one form of an end behavior model. The degree in the numerator is less than the degree in the denominator. This has a degree of 1, this is a degree of 2. So y equals 0 is the end behavior model. It is a horizontal asymptote. Okay? We'll talk about the x and the y-intercepts. Remember, the y-intercept's always the easiest to find. The y-intercept, we simply plug in 0 for x. If I plug 0 in for x, and I know I'm sliding up and down here, but if I plug 0 in for x, I get -2 over -5. Negative over a negative is +2/5. Where x-intercept, here's a nice part about rational functions. X-intercepts occur when the numerator equals 0. Not when the denominator. I could put 0 here, multiply the denominator up. It's the same thing as setting the numerator equal to 0. So when x equals 2. So that's why we always want to find the x-intercept and list it as a coordinate point. It gives us 2 good points to shoot for. Okay? So let's dot this in. This is going to have some unique characteristics to this graph. Always start by dotting in your vertical asymptotes. X equals 1. X equals -5/2, -2.5, 1, 2.5. Okay? Then dot in the horizontal asymptote. Y equals 0. There it is. Then plot those intercepts that I asked you to find. Here is 2, 0. I'm going to do it a little bit darker so you can see it. And then I have the point 0, 2/5. All right, we have 2 points to shoot through. Here is the key to this when we're graphing it. I have this horizontal asymptote. If I plug a number like 3 in, I'm going to get 1 over a fairly large positive number. It's going to be really close to 0, but it's going to be on the positive side. It's up here. And this has to approach this horizontal asymptote. That's the definition of a horizontal asymptote. As x goes to infinity, this graph's going to get closer and closer and closer. So really what happens is this comes back, it has to be getting larger this way, and this has to cross through and go down here. What? We're crossing through a horizontal asymptote? Yes. You can cross through a horizontal asymptote. Typically, if you have an x-intercept on the outside of the vertical asymptote, that's when you'll see these. I call this a very fancy term. We're going to have a bump here. Really, it's a maximum. We're going to have a maximum point over here to the right of this vertical asymptote. But now, notice, this is 2x plus 5 to the first power. This is x minus 1 to the first power. These are both poles. So I have to climb the pole before I start my graph. I have to go through my y-intercept, but there's no other x-intercept to go through. I cannot cross the x-axis. There's no other x-intercept. So I have to turn around and go back. I have to slide down the pole before I start again. There it is. Okay? Let the points guide you. Work it from right to left and just let the points guide you, knowing that we may get a bump to the right or left of a vertical asymptote. Okay? A maximum or minimum point. Let's take a look at this one. The degree on top equals the degree on the bottom. We have a quadratic over a quadratic. So I look at the coefficients of the highest degree terms. 3 over 1. Y equals 3 is the end behavior model. It is horizontal asymptote. Okay? What about vertical asymptotes? Again, let's try to factor the numerator and the denominator. I'm just quickly going to say 3 times 5 is 15. There aren't two numbers that multiply to be positive 15 and add up to be negative 1. Therefore, the numerator is not factorable. But the denominator is, it's x plus 2 times x minus 2, which means, again, we have two vertical asymptotes at x equals negative 2 and at x equals positive 2. They are both poles. They are poles because x plus 2 is raised to the first power. The factor of x minus 2 is raised to the first power. These are both poles. Okay? Let's just go ahead and complete the x and the y intercepts while we're down here. X-intercepts occur when the numerator equals 0. 3x squared minus 5x plus 5 is non-factorable. So you'd have to try the quadratic formula. But when you try the quadratic formula, if you just look at the b squared minus 4ac part, you get a negative number. Okay? So the discriminant tells us it's negative. There are no x-intercepts. None. Because 3x squared minus x plus 5, which is the numerator up above, never equals 0. The y-intercept's easy to find. Plug in 0 for x. If we plug 0 in for x, I think it's easiest to do it in the original is 5 over negative 4, or negative 5/4. There's a good point to shoot for. I'll write it down for you. 0, negative 5/4. All right, we're going to take this information, we're going to graph it and get a nice sketch. X equals 2, x equals negative 2. Right here, x equals 2. X equals negative 2. Okay? Graph in your horizontal asymptote, which was y equals 3. Okay? Do we have any x or y intercepts to help guide us? Yeah. We found the y-intercept to be 0, negative 1 1/4, negative 5/4. is right there. Okay? There are no x-intercepts. Just using this point right here. I cannot go this way. I cannot cross the x-axis. Using that one point as my guide. The graph has to go here and here. I have to climb the pole before I start again. I have to approach the horizontal. This asks, do I have to climb the pole before I start again? And we can sketch this nice graph. One last one. And then you can work on the worksheet. The degree on top is larger than the degree on the bottom. To find the end behavior asymptote, we have to do long division. On this one, you could do synthetic division. And if you did, you showed that work, that would be fine. But I'm going to do long division just so we can see. What do we have to multiply x by to get an x squared? An x. X squared plus 2x. Here's where a lot of students make a mistake. They'll subtract and then add, and they think that it's 0. Nope. I'm never going to say subtract. I'm going to say change the signs and add. Negative 2x minus 2x is a minus 4x plus 3. What do you multiply x by in order to get a negative 4x is a minus 4. Negative 4x minus 8. Again, I'm not going to say subtract. I'm going to say change the signs and add. Plus 11 over x plus 2. But remember, when I'm looking for end behavior model, as x goes to infinity, the bottom grows larger than the top. The numerator does not grow as fast as the denominator. If the denominator grows faster, that goes to 0. So y equals, and you have to say y equals, x minus 4 is my end behavior model. That is a slant asymptote or a linear asymptote. I wish they would just call it a linear asymptote in pre-calculus, but you're more familiar with slant asymptote terminology. I just like linear because then we have parabolic and cubic, and we can just continue with that. Okay? So give everybody a chance to write that down. Vertical asymptote. What value of x creates a 0 in the denominator? X equals negative 2. So I'm going to put that right here. Good. As you're looking at your paper, remember, x-intercepts occur whenever the numerator equals 0. X squared minus 3x plus 3 equals 0. I'll kind of show this a little bit here for you. X-intercept when the numerator equals 0. We hope that it's factorable. But there aren't two numbers that multiply to be positive 3 and add up to be negative 2. It'd have to be negative 1 and negative 3, or positive 1 and positive 3. It's not going to work. Again, don't do the whole quadratic formula. Just check b squared minus 4ac. 4 times 3 is 12. That's negative 8. You can't take the square root of negative 8. That's the discriminant. That's the part of the square root. You cannot take square root of a negative number. So there is no x-intercept. This is none. Y-intercept. Here it is. Plug 0 in for x, you get 3/2. You can write that as 1.5 if you want, because that's what we're going to need when we plot this. I'm going to use this information right here. I'm going to start with my slant asymptote. Here we go. My slant asymptote. Graphing this picture now. I had a slant asymptote that had a y-intercept of negative 4 and a slope of positive 1. So I dot this out, and I dot it all the way out so I have good accuracy. Going up 1, back 1. Okay? You want that slant asymptote to be nice and straight. A straight line, a straight edge would be preferred. Vertical asymptote, you can look down there, was x equals negative 2. we do not have any x-intercepts. So there's no x-intercept along here, but we did have a y-intercept at 0, 3 halves. You can look down below. That's 0, 1 1/2. That 1 point is enough to tell me I cannot cross the x-axis. It has to approach this vertical asymptote. I'm not going to cross the x-axis, so at some point here, it's going to turn. It's going to approach this slant asymptote. And the fact that I know this is still a pole, because the denominator was x plus 2 to the first power, means I can slide down the pole and start again. There it is. Done. Those are the two pieces to this. And you graphed these last year. But again, you didn't talk about a pole and a volcano. If you know the difference between that, you can identify pole versus volcano. Graphing these becomes significantly easier because you know how it's going to approach the asymptote. So if it asks for the limit, what is the limit as x approaches 2 from the right? It's positive infinity. What is the limit as x approaches 2 from the left? Negative infinity. That's it. Okay? Work on that worksheet, and I'll have a video out on that as well.